Hi everyone, I'm Ming Lang. So today we have two talks as usual, both from Europe. So our first speaker is Felipe Rocha. He's a postdoc fellowship in the Applied Math department at EPFL since 2019 under the guidance of Professor Bulfa and Professor De Paris. He finished his PhD and master's degree in computational modeling at the National Laboratory for Science Computing, Brazil, under the supervision of Professor Paulo Blanco. And he has begun his research career mainly interested in the computational mechanics of soft tissues, computational homogenization, and recently he's interested in reduced order modeling and machine learning, and actively exploring these techniques to enhance computational homogenization in solid mechanics. So today he's going to give us a talk entitled DeepBND, a machine learning approach to enhance multiscale solid mechanics. So please join me in welcoming Felipe.
Thank you so much for the nice introduction. I'll try to share my screen. Is it still disabled for you?
You may share your screen now.
Yeah. Yeah. Can you see?
Good.
Good. Okay. So as Ming Lang said, my talk today will be about computational homogenization, but enriched with deep learning approach. So this work was done at EPFL in collaboration with Simone De Paris, Pablo Antolin, and Elisa Buffa. So first I will start with a little bit of a motivation, a lot biased because it's my field, but computational homogenization could be applied to more applications than they will show here. I will introduce the formulation of solid mechanics, multiscale solid mechanics. Then I will formulate the methods. I will explain about how reduced order modeling will be coupled with deep neural networks to enhance boundary condition in this case. And I'll talk about the dataset generation and the training. And after I will show some numerical examples. So as I said, my motivation is a little bit biased because this is my work of PhD, was in computational homogenization of cardiovascular tissue. But you can think in any heterogeneous materials, for example, a reservoir, oil reservoir, or bones, for example. There are, you name it, there are a lot of physical systems which have lower degrees, heterogeneity in the lower degrees at the spatial scale, and also time scale. But here, let's focus on spatial scale. So you can see, for example, one artery is composed by smaller components, for example, fibers and cells, for example. So basically, our kind of modeling will be in continuum. So our kind of problems are continuous in one scale, let's say the macro scale, the coarse scale, and also continue in the smaller scale. And the computational homogenization approach basically means that in order to evaluate constitutive laws in one scale, this will be done by an auxiliary problem in which I apply some homogenization rules, and then I recover, for example, stress states, so tangent tensors that we call homogenized tensors. There is a bottleneck in this approach, is the computational cost, because it's a what we call FE square approach, which means we do finite element, in this case, in the two scales. So the computational burden explodes. So one problem of interest is reducing the size of the the window that we analyze. And this normally cannot be done because of some errors due to boundary conditions. So this is what I explain here. So the name of this error is resonance error. So this is basically ruled by two factors: the boundary condition effects, and also when you decrease or increase the microscale domain, you increase the sampling. So we still have to have a good sampling of the material, and with good boundary conditions. So one solution, as I said, is to increase the domain, but this is very computationally expensive. We can keep the domain, and then we can do a multi-cale approach. We can average solutions, and I decrease the error due to the sampling, the error 1 that I call here, but the boundary condition is still the error of boundary condition is still present. And this is what I will show here: choose a better boundary condition. But how? This is not very well. It's not very easy to do since we lack of physical knowledge. So my idea here is to use deep learning to enhance this part. Choose better boundary conditions. So the problem is the infinitesimal elasticity problem in the macro scale, and also in the micro scale. And as I said, with some boundary condition, I will show next. So one thing that we have to do here is to couple the two scales. Here I use the method of multiscale virtual power. There are plenty of methods. I chose to use this. And basically it's based on the kinematical coupling, based on these ansatz. It's basically the one displacement field in the microscale is composed by a linear decomposition of displacement fields coming from the macro scale plus some fluctuation field. And then we have to suppose some kinematical constraints. This is here the average of displacement in one scale is equal to the displacement in the other scale, and also for the strain. And then this is in terms of kinematics. In terms of stresses or powers, we have also the balance of virtual power given below. So this gives rise to one admissible space for fluctuations. It's basically this space, zero average, and also the tensorial average on the boundary. And also the auxiliary problem, what I call corrector problem. This is basically the weak version of the microscale problem already given here. And also a formula for the stress, which is the average in the cell. Also, instead of the stress, we can deal with the elastic tensor. This is more interesting here in our problem. This I have to solve the problem for each unit direction, and then I can assemble the homogeneous tensor. As I said, the minimum set, the admissible set, is given by these two restrictions. Of course, I can have more restriction and then have different models. So, for example, one very used model is the periodic one, which basically it's the most standard in literature. This model have a good compromise between the stiffness that we get at the end, and also the linear model, which is basically Dirichlet homogeneous condition on the boundary for the fluctuation. So here, as we said, we have a not very, let's say, certain kind of boundary condition that guides us. We do have some guide rules, and when we don't know nothing, we basically choose the periodic case, which is not that optimal. So our approach here is.
Felipe, can I ask some questions? Like, for
Yes,
example, do you have the option of doing like the Schwarz method to pass like displacements and get stresses back and so on, instead of the periodic?
What Schwarz, you mean?
The Schwarz method for domain decomposition.
Domain decomposition.
Yeah.
Yes, but this is based in an iterative coupling, right? Yes. So the idea here is a little bit different. Is we uncouple the problems in order that we can solve in parallel. It will never couple them back.
I see.
So in this case, we don't have this, let's say, a better choice.
Okay.
The Schwarz method is interesting. It basically this space can be used by to let's say motivate the Schwarz method, but we need this iterative.
So eta here is what? Displacements, because you for everyone here to understand, because you have all these notations that you didn't actually.
Yes.
Eta here is displacements, right?
Eta here is displacements, is indeed fluctuations. So is what I said here. I'm dealing with these variables because these two variables are given from one scale to the other, and the only variable which is not given is the fluctuation. So eta here represents fluctuations indeed.
Of displacements. Fluctuations of displacement or fluctuations of displacement. Okay.
Yes. Displacement unit. Yes, exactly. Shall I move?
Please.
Yeah. So the idea here is to use previous computations in order to enrich and predict a better boundary condition. So I'll show how we do this. So first, I will rewrite the problem in terms of parameterized PDEs, right? So in this problem, the parameters for me will be parameters that describe the material in the microscale, and also the strain, the macro scale strain. Right? So these are my two kinds of parameters, and my high fidelity model. It is the problem solved in a bigger cell, right? Using periodic boundary conditions, which is the best that I can simply choose. This is done in a much bigger cell, and I will show the size of the cell that we do. And then we want now to use this problem and reduce the problem. This is done by taking the test functions as 0 out of in the complement of omega r, and then the problem becomes a problem with Dirichlet boundary conditions, and this the boundary condition should be provided by some method, and we will use neural networks to provide this boundary condition. So basically now this new space VR, right? It's basically one space that I have some oracle that gives me boundary conditions. Basically, it's imposed. So the parameterization of the constitutive law here, we choose a very particular form. It's one constitutive law composed by two materials, linear elastic, and then I'm assuming there are two phases, and one phase is given by union of both. And so the parameter set here is only the radius of the balls. This is to reduce the let's say the number of parameters of the problem. Also, the parameterization of macroscale strain. I choose like the Voigt notation. Basically, it's my parameterization is that. And then I also see that the problem is linear, so the solution would be linear at the end. And then I will exploit this on my neural network architecture. There is also something that I will exploit on the neural network architecture is the symmetry. So basically, we see that the vertical load and the horizontal load is related by some symmetry. Basically, if I rotate the parameters somehow in inverse order and then rotate again the solution, I will obtain the same solution. So I'm using this transformation here as well. So the problem now is...
sorry to interrupt. Can I ask a clarifying question? Because there's a lot of notation here. Where, for the machine learned imposition of boundary conditions, where does that come in? Is it attraction on the macro scale?
Yes.
Output of the neural network?
Yeah. In this problem is a Dirichlet kind of boundary conditions, displacement.
A displacement, okay. But
yes.
It's on the boundary of a macro cell. Is that right?
Yeah, yes, on the microcell, yes. On the boundary of the microcell. Exactly.
And then how does it couple back up to the macro cell? It comes up through a boundary, through a volumetric term?
The couple with the macro cell is given by the homogenization. So after the problem is solved, I obtain the stress, homogenized stress, and this will be used in the macro problem.
And it adds, yeah, I got it. Okay, thank you.
If here the problem is linear, so there is no like iterative process. But if the problem is non-linear, there will be an iterative process.
Are you going to tell us how you train the network? Who gives you the data and how you do that? Are you going to tell us that, or?
Yes. I will.
Okay.
Yeah. So here is our idea to parameterize the space, right? To parameterize the boundary condition. So basically, is a boundary condition given by a linear combination of a neural network with some functions that are reduced basis. That I will show how we obtain those. Basically, there are functions based on the data that I have, on the data set that I have, that better describes the situation of the boundary condition for that specific data set. Right? And then using the linearity, I also get that the neural network is only dependent on the constitutive parameters and not dependent on the macro strain. So I reduce the number of parameters of the neural network.
Can I make a comment here? So some data who is doing similar work in Midland would know. This is exactly the DeepBND. What you wrote here is a DeepBND.
Okay.
The NP is the branch and CI is the trunk.
Yes, but I'm not using generative.
No, it's not generative. It's anything, but some data knows what I mean.
Yeah, of course. Here I'm a little bit simpler on the neural net side. Let's go. So this idea is not mine. There are some works being done like since 2018. by Gestaven and the parties, for example, that use the reduced base decomposition to and neural networks together. What's new here is the use to predict boundary conditions. This is basically my contribution. The nice thing about reduced base is that we have the control of error. There's a nice theory behind all of this. So the general framework is basically the basic general framework of reduced bases. Basically, is based on an offline phase and an online phase. First, I have to generate a data set, extract the reduced bases, and then in this case, I train a neural network to give this nonlinear mapping, and then given this neural network, and given some microstructure that I want to use, I predict the boundary condition, and I solve the microscale problem with the predicted boundary condition, and then I originate the solution. So basically, the new steps here are step 4 in the offline phase, step 1 in the online phase. So I can remark that this is, let's say, not intrusive. It's very easily implemented to existing codes, let's say. So yeah, it's just other layer of abstraction. So the data generation, I'm using lattice hypercube to sample 36 parameter set. 36 because I have 36 radius here. I'm using this as the big window, and I'm the smaller window we're using 2 by 2, so four inclusions only. So I will show that with this kind of approach, we can get the same orders of error of a 36, let's say, window, with only a 2 by 2 or 4 inclusions window. We get more or less the same order of error, and of course, much smaller in terms of computational time. I'm using these parameters, and I'm using a contrast of 10 between the phases. And then here I give a little bit the idea of computational costs. And then I also simulated one data set for training, and also is the same that I use for the RB extraction. And I also some validation data set, some test data set. So
before you move more into the, you had a slide about the symmetry of at the boundary and how you treat that. So do you set it up so that if 2 elements share a common face, they get the same Dirichlet condition? Because there's a question about momentum conservation if the tractions are equal and opposite.
Yes, this is a nice question. Indeed, those windows never touch each other because we are in a much smaller scale. So since they don't touch each other, so we have what we call separation of scale. So we now have this case that we have to couple, look to the neighbor.
So this is more like a representative volume element.
Yes, exactly.
2 touching subdomains that are, got it. Thank you.
Yes. Exactly. So the reduced base is obtained by the POD algorithm. It basically, given the data set, I need to construct the predilection matrix. I need to perform some eigenvalue analysis, and then I determine those bases up to a certain number. And then I also have a control of the error. So I know exactly the error that I'm doing. So I choose this number based on some tolerance that I have to set. I will show next. And then I have a set of boundary of reduced bases. So one important thing that I forgot to tell you is that I do two kinds of data sets. I do one for the actual load and one for the shear. And the one for the other direction of the actual load, I don't need to do because I use the symmetry. So here I save one data set, I save one neural network. Yeah, I reduce the size of the problem. And yeah, so here for the two data sets, I basically have the same behavior for the reduced bases. Basically, they decrease more or less in the same rate. So that means I can use the same kind of neuron, same size of neural network. They have the same complexity. So here I'm putting the threshold at 10⁻⁸. So basically, I'll show. Yeah, I'll show a little bit next. So the architecture here that I'm using is basically one neural network. Here is feed-forward nuclear perceptron for the actual load, other neural network for the shear load, and then I use this combination of same neural network plus rotation, and then I combine this what I call a RB layer, which is basically the linear combination. So the error that I'm doing here, that I'm interested in, is the L2 error on the boundary of the fluctuations. So as these bases are orthonormal, I can decouple them like this, where here is the projection onto the RB bases. And then what I have here, the neural network error will be ruled just by this part, and the other part would be the error intrinsically to the POD that I have control of this, and this one will be given by depending how good is my training. Of course, I'll show here. There is a trade-off between the number of reduced bases and the total error. So for example, here in orange, I see the total error. So the total error for very few reduced bases is ruled by the POD error. So the POD becomes to be interesting when basically the POD error is low. And then I checked here that with more POD, I do not increase the DNN error. So here, basically, I reach a steady state case scenario, let's say. So here, what this plot tells me that basically doesn't matter if I take 40 RB bases or 240. Basically, I have the same error at the end. So I take the 40 RB case. And then, of course, my neural network will be much smaller. And then I'm using these parameters, 3 hidden layers with 30 neurons each. I will have 36 neurons in the first layer because I have 36 parameters, and then 40 on the last layer because I have 40 projections. And I'm using swish as activation. I'm using dropout and L2 penalization for regularization, Adam optimizer, with some adaptivity on the learning rate, and mini batch. Here I have some results. So basically it's not overfitting. Just to check this.
Felipe, how did you generate the data in the first place? Did you run very fine resolutions, or what did you do?
Yes, I'm sampling the parameter space with the latency hypercube, Latin hypercube. So basically, yeah, and the data is generated by this simulation here, and then the data that I want to predict is a trace on a boundary, right? So the internal boundary. So I simulate this bigger cell, and then I just store and use the solution on the boundary.
But I have a question. So I was wondering if, let's forget about all this good math and the neural networks and so on, and we just simply do a phase field for this problem simulation. Do we get good results? Can we beat the phase field for this? After all, it's a stationary, I mean, you can have a different phase of these inclusions, and then it's not a big deal. I'm oversimplifying, but I'm just trying to get some reaction from you.
Yes, I think is about the computational cost, the main reason here, because if you want to do phase field, you have to mesh at the size of one phase, right?
Yeah, sure, of course.
Yeah, so and this you could not solve in parallel.
Right.
Maybe a similar question is, there's many works right now where people are trying to machine learn in an effective Lemay coefficient, for example, right? Like you just want to learn how to add a little bit of stiffness to an element in order to match the microstructure. Do you expect that what you're doing gives something like, how can you help us understand how this would compare to an approach like that?
Yes.
Like if this exposes something that you can take advantage of?
Yes. So this is a really nice question. I put on the conclusion indeed. So my approach, I see my approach as a intermediate step. I'm not replacing the full problem with a surrogate model. So I'm still using the model, but this model have less errors. And then I can use smaller cells. Then I can solve faster. So, but I always have the model there solved. So I have a better solution because I still solve the problem. This is my view of the problem. Yes, indeed, there are a lot of works by replacing the multiscale homogenization by surrogate model. This is valid, right? Indeed, for linear elasticity, this is not such a big deal because indeed we can let's say learn the solution. There's not a big deal. The big deal is when you have nonlinear elasticity with story dependent materials. Then it's hard to generate all the data and learn the model because we have so many paths and so on. We have an infinite number of story previous histories. So my approach, I think is I haven't done yet, but I think is a good candidate to decrease the computational border of nonlinear models, basically. Hi.
Please go on. Please go on.
Okay. So I arrive on the numeric examples. Then I think it will be better understood. So here, my numerical examples is using F2 FE square simulations. So what does that mean is that for each Gauss point in a finite element, for example, I choose one microstructure. And this microstructure is not the big one, is a smaller one to my problem. And of course, I compare with if I choose the bigger one, right? I will show the results. And here I'm solving the Cook membrane. It's a benchmark problem in solid mechanics. And the microstructures are chosen randomly. And I do 10 realizations. It means I choose randomly differently 10 times for each Gauss point. And yeah, I also do for different mesh size. And then what I want to compare is how good is my accuracy if compared with periodic conditions, and if compared with high fidelity solutions, and how good is the computational cost compared with periodic condition, because I'm using the same size. No, compare with the high fidelity model, right? Because I'm using a big size. And then this third question is we answer next is how does that compare with the direct numerical simulation, which is if I solve, if I mesh the smaller scales and then I solve it, then I will show in the next example. So here, these are the results. In blue, I have the high fidelity solution. And in cross, I have the periodic, and in orange, my model. So it's closer to the high fidelity solution with the same computational burden as the periodic, basically. This I'm comparing the displacement of one of the point A here. And I also compare the von Masi stresses and so on. So what I get basically is, in terms of errors, I have basically 2 orders of magnitude less for my method compared to the high fidelity solution. In some cases, in other cases, 1 order, basically. It is in relative errors. And in terms of speed up, I have about 60 times less compared to the high fidelity, to the problem solved with the bigger cell, right? So the high fidelity model. So basically, what I solve is 0.005 seconds. I solve in 3.3 seconds. So it's a 60 order of magnitude. Of course, this is just for one cell, but if I do in a fine mesh, I have to solve for each cell. Of course, I have parallel computers, but I don't have, let's say, 1 million. Let's say it's not so easy to find a computer like this. So I'm using here a 32 cores computer. Here I'm comparing visually the von Masi stress. So here on the right, we see the periodic. So you can see a lot of, let's say, noise. Let's say you can see there are more noise than the other ones. Of course, there are noise because each point there are different microstructures, so there are some noise. But we can see the difference. It's really visually understandable. So basically, between the DNN, our model, and the high fidelity, we don't see any difference usually. And here, like in terms of error, so basically, our method gives let's say, 10⁻⁴ in error, in the relative error for each stress, more or less, and the other 10⁻². So basically 2 orders of magnitude in the stresses. So the next example is I'm comparing with the DNS solution. So basically, the DNS suppose a bar like this, right? And here I have 7 inclusions on the vertical direction. Actually, I'm doing for 24 and 72, the example I'm showing here, but just to depict, I'm using 7. And then for each Gauss, and then I have two meshes, right? One mesh of one really fine mesh, like the DNS mesh, and one a coarse mesh like this, right? That for each Gauss point, I take the cell which is closer to the center point of that mesh, right? So the parameters that I use, I take from the let's say from the mesh using in DNS, and then I will compare these 2 solutions, and then I have the solution obtained by the high fidelity model, which is with the bigger cell, and then a solution obtained with our approach, which we reduce the cell but use a better boundary condition. Then I'm applying vertical loop like this. So what I get here in terms of relative error is basically in blue. My method is basically is in a much smaller order than the periodic, right? And closer to the high fidelity, right?
Hi, Philip. Yes, sorry for interruption. So my name is Henry, and I'm a PhD student in George's group. Yeah, so I have a question. Maybe I missed something. What is the relationship and connection between the DNS and high fidelity and your reference solution, which you mentioned a few slides ago? Yeah, I'm kind of confused on these 3 concepts in your presentation.
Yeah, let's go. So first I have the DNS. The DNS solution is the finite element solution of a mesh, of really fine mesh, the mesh of the order of the heterogeneities. That's a really fine mesh. And then I have the computational homogenization approach, in which I have a coarser mesh, and for each Gauss point, I have a microstructure. How this microstructure is chosen based on this problem, right? So basically, I have the Gauss point, and then I choose the one which is closer to the, let's say, the window which is closer to this Gauss point, right? And the high fidelity solution is the 36 6x6 window, right? And the other solutions, the periodic, is the periodic with 2x2 window, and the periodic with the 2x2 window with the new boundary condition. Okay. So basically, I have one simulation, the DNS. So this is one solution. One and more 3 cases here. One, the high fidelity, which is the bigger window, the periodic in the smaller window, and the enhanced boundary condition. So I have 3 cases. And then I'm comparing these 3 cases with the DNS.
Okay, yeah, I got it. Thank you.
Okay. And I compare the L2 norm of the old solution, and also the displacement in some points. So basically, I have these results. This is for the case in which I have 24 inclusions on the vertical direction. Though the computational homogenization solution will be closer to the DNS if I have a lot of inclusions, right? If I'm decreasing a lot the size of the inclusions. which is not the case here, because otherwise we could not solve the DNS because we explode in terms of computational power. So I'm using just 24 and after 72. And in the 72, I got a surprising behavior indeed, but in the good sense, that my new boundary condition gave better results than even the high fidelity model. So this was a little bit unexpected for us, but well, we are happy that it was not the goal, but even in terms of accuracy, we got better results. And of course, in terms of computational power, yes, we have 60 speed up. Yeah, and again, the periodic is in the smallest cell is the worst, as expected. Right. So the concluding remarks are, yeah, we are basically proposing a neural network which is physically inspired because it still solve the problem, but specific for numerical homogenization. This boundary condition is data-driven because we base it on previous simulations. As I said, it was one question. My method, I see the method as an intermediate method between fully replacing the multiscale problem with surrogate models and standard computational homogenization, which is too expensive. So my method is in between. Yeah, the architecture was tailored to exploit symmetries, as I mentioned, and previous knowledge, because I learned the reduced basis from previous knowledge, and then I use this. Yeah, as I said, 60, more or less 60 in the speed up, and basically the same order of magnitude in terms of accuracy. It's easy to implement. Basically, yeah, I have a library for this code in Phoenix, a very simple library, and then it's really easy to implement. I will show, I will provide this in some weeks. Yeah, the problem was here was restricted to the solid mechanics, but indeed the method is general, could be applied to other problems, other interesting problems, for example, porous media or fluid dynamics, and also different kind of heterogeneities. Here I choose a very specific one to reduce the size of data sets, but then we can parameterize in a more richer way the microstructure depending on the applications, of course. Yeah, so for those who want to explore more, I have some reference, and this basically the work that I show here is available in archive. Thank you.
All right, thank you, Philip. Any questions from the audience?
I have one last question. So this is Nat Trask from Sandia National Lab. For the Cook membrane problem, it seems the thing that's really nice about your approach is that it's rooted in a good discretization of what's going on. And I'm curious, so this is like the canonical problem for handling near incompressibility. And I'm curious if the microstructure is near, did you do any experiments with that where the microstructure is near incompressible and whether other approaches would fail and yours would not fail?
Yes, indeed, yeah, indeed, it's a popular example for incompressibility, but this is not the case here. I chose this problem because, let's say, when you see the stress fields, we have different kind of stresses in different parts. So basically, it's a, let's say, rich problem to solve in this sense. But here I'm not exploiting any incompressibility. Indeed, the Poisson ratio is about 0.3, and this is imposed on the microstructure. Of course, when you homogenize, we can change a bit, but doesn't change a lot. So it's not any incompressible here. Would be let's say interesting to see incompressible results, but let's say I'm not dealing in terms of numerical methods, right? And I'm not proposing a new numerical method to solve incompressible problems. So let's say I don't expect any improvement. Let's say I think it will be as good as the numerical method that you use. And if your numerical method is good, then I think we're gonna get the same results as I have.
Yeah, I guess the suggestion is that someone else who instead was just trying to learn a homogenized Lemay coefficient, if you're right at the boundary of incompressibility, it might fail, because they're trying to learn the material property, and that's where something pathological happens.
No, this is nice.
We're learning the boundary condition of the microstructure, so you're not breaking anything, and you're not in danger of extrapolating out past Poisson ratio of a half. So just a suggestion. I feel like that might be something actually.
No,
really
this
nice.
is a nice. Yeah, I haven't thought about. Yeah, this is a nice suggestion because still there are the physics. So yeah. Okay. Thank you. Thank you a lot.
Felipe, all these are steady states or quasi-static, right?
Yeah, this is static. Yeah.
Do you have any ideas how to do this for time-dependent problems? Multiscale in general, homogenization for your problems, not in general, but this for time-dependent problems. What would you do, and how easy it is?
Yes. So, for example, here for time-dependent problems, the standard approach is in reduced basis is that the reduced basis is not the same reduced base for each region of the time. So basically, when you move,
that's why I'm asking.
When you move in with the time, you have to incorporate new reduced bases and so on. So yeah, so as I see, the problem is that you should identify some scenarios and then train. Get some reduced base for this scenario, and then train a neural network specialized for this reduced base for this scenario, and then change over time, basically.
But are you suggesting that the cost to construct the reduced bases will be too much, or it can be done? That's the thing I don't understand. It will still be very competitive, or even better than the full DNS.
Yeah, this is something that I'm working on in the moment, because here I constrained a lot the heterogeneity. So it's a circular phases and so on. I know the position and so on. So if I have more heterogeneity here, more rich heterogeneity, so the number of snapshots will explode. Everything will explode. So it's not clear for me how I can do this, right? If my heterogeneities are too flexible, let's say. Yeah. So this is, let's say, open, let's say, because of course, for example, yeah, you're going to use this method since you need to simulate like several number of times some structure. For example, I don't know. We're gonna if you want to optimize a structure and so on, So you will be this neural net, this new boundary condition for one kind of material, for example, and then this material will be fixed, and then you can use it to optimize your structure. So you change. The problem will change a lot, let's say, over the iterations of optimization step, for example. So yeah, so the model will be reused so many times, so that pays the cost of generating the data and train the neural network. So this is supposed to be used in this scenario.
All right, thank you.
Yeah.
Midlang,
Thank you a lot.
it's 1 o'clock, so maybe you can.
Sure. If there's no more questions, so let's thank our speaker again. It's a very nice talk. So let me introduce our second talks. So the second talk will be presented by Professor Ioannis Stefanou and Dr. Filippo Masi from ECN in France. So Dr. Ioannis Stefanou is a professor at ECN France. He finished his PhD at the National Technical University of Athens on studying civil engineering, mechanics, and applied mathematics and geomaterials. So his main research topics are the mechanics of geomaterials, structural dynamics, geomechanics, fault reactivation, and earthquake control, etc. And he's also the PI of many large projects, for example, the ERC STG project, and also the Connected Talent project of controlling extreme events. And Dr. Philippe Masi is a postdoc researcher at ECN France too, and he studied computational mechanics and applied mathematics at the University of Florence, and then he did his PhD at the Central Nantes. He's interested in the data-driven modeling and machine learning for constitutive modeling of material and the geomechanics. He received his thesis award by the French Computational Structural Mechanics Association and of his university. So please join me in what? Oh, sorry. Today he's going to they're going to give us a talk entitled "How Machine Learning Can Help in Earthquake Control and Fault Mechanics." So please join me in welcoming their presentation.
Thank you, Minglang, for the introduction and the presentation, and also for the invitation. Also, I would like also to thank Felipe for the very nice presentation just before. Maybe I will start sharing my screen. So, well, the idea is just to give the big picture at the very beginning about where we would like to go generally, and then I will leave, I hope, a lot of time to Filippo to explain some recent developments on TAN. So I don't know, you see my screen? Everything is okay?
Yes, we can see your screen.
All right, great. So in the target in the COQUIC project is to answer to a question: if we could, in a day or in the future, let's say, to control the earthquake instability. So this question is addressed in this project, and what we would like to see is if this is finally impossible, or if it might be just impossible. But the target here is not to just have an idea; it's to prove if it is impossible, or to prove if it is just impossible. Well, the applications behind the impact regarding the geosciences, earthquakes, society, engineering in general could be quite important. Before thinking of that, we would like to answer this question, providing some mathematical proofs and some experimental evidence of one or the other way. So for this, we need to use mathematics, mechanics, physics, and experiments in order to answer to this question. And in this general framework, there is a new way of doing homogenization and modeling materials with complex microstructure that we call TAN. Of course, there is a lot of inspiration from the seminal works of your group, and I'm referring to PINS. And this is something that Filippo will show and explain in some minutes. But just before, I would like to refocus to earthquakes. Earthquakes is a dynamic instability. So what happens is that due to the movement of the tectonic plates, you have the accumulation in the Earth's crust of huge amounts of energy. So you can see here in this simplified figure of a fault, you have the fault in the middle, and around it you have a rock. And as the far-field tectonic displacements accumulate and evolve, you have this increase of deformation, increase of straining, the increase of the elastic energy, and the specific point, the friction that the fault provides here. I hope that you can see my cursor. If it's not the case, just tell me. It will break. Some conditions of instability that we can describe mathematically if we know exactly the system will happen, and then we'll have an earthquake. This dynamic instability means a big rupture at the level of the earthquake fault, and then you will have a very small portion of this energy, or that's of around 1 to 10%, that will travel to the surface and will destroy our infrastructure, buildings, will kill people, will create tsunamis, and all these disastrous phenomena that we have. And something similar happens also in induced seismicity. Probably you have heard about what happened in Oklahoma, that humans now, we know that we can reactivate faults and provoke earthquakes if we inject fluids in the Earth's crust. Now, the target here is to control a dynamic instability, and people coming from electrical engineering, when they listen probably to control, and not only, of course, in engineering more generally, also mechanical engineering, when we combine control and instabilities in the same sentence, it might ring a bell about what control, the mathematical theory of control, could do. But in order to control the systems and to incite them to follow specific trajectories that we would like to. But in order to do so, the systems should have an input. Well, I think that humans were quite lucky in the system, in this dynamical system, because when we inject fluids in the earth crust, we change the friction. You see here that this is the Coulomb friction that I just showed you in some schematic, very simplified expressions, that depends on the normal force, normal stress that it is developed over a fault area. Now, that means that if I increase the fluid pressure, let's say I inject directly on the fault, or in the vicinity of the fault, or even some kilometers away from the fault, provided I will wait enough for diffusion phenomena to take place, then I will change the friction. And therefore, if I change the friction, there might be a way to control the system. Now, I won't get into the mathematical details of the theory that shows that for this specific dynamical system, that it is dominated by friction and other uncertainties, because we cannot really measure what happens deep down there. We have done some proofs, but I will show you some of the results that will be also presented in the defense of a couple of PhD students of mine, in particular George Georgopoulos and Alexandros Stathas, that they will defend in mid-December. I will show you an example of robust control of earthquakes. So I will show you the example of a strike slip fault, more or less the case of San Andreas, but imagine it a bit shorter. So we take a fault that is around 5 kilometers length with, in this simplified example, 5 kilometers depth. And we assume a friction that is unknown for us and heterogeneous over the whole fault area. Around the fault, you need to imagine that you have an elastic half space that extends to infinity. And what we would like to do is to adjust the fluid pressure all over the fault in order to avoid the dynamic instability, that in this case is of a magnitude of 6, An earthquake of magnitude of 6 corresponds to around one bomb of Hiroshima that comes to the surface, if I remember well, the scalings, but it is huge already. And if we leave the system, just to show you what happens, if we will leave the system uncontrolled, you'll see here the displacements on the right that they develop in more or less 5 to 10 seconds. It's a slip of 2 meters, accompanied also by the velocity that is of the order of 0.7 meter per second. So now 0.7 meters per second might not be very high, but if you imagine that you have a huge block of 5 times 5 kilometers that moves with this velocity, the energies are enormous. So now we apply our mathematical theory and we control the system. And you see here in these 4 plots, these 4 animations, on the bottom right, you see with the dotted line a trajectory that we prescribe on the system. So this is the average sleep that we prescribe, and we want the system to sleep, but in this time very, very slowly. And with the blue curve, you see the average pressure that has to be developed all over the fault surface in order to allow for this slow sliding to take place. And on the top left, you see that the velocity that is developed, it is of the order of 0, because by design, the sleep is controlled, and instead of having a very fast dynamic instability, now you have a very slow sleep by design. And on bottom left, you see the profile of the pressure that had to be developed over the fault area in order to control and inside this very slow sleep.
So
now,
Ioannis,
yes.
the control is, what's the control mechanism here? By injecting fluid or what?
Exactly, injecting fluid. Yes, we inject fluids and we provoke a very slow. We are at the verge of instability, meaning that if we leave the system alone, it will break like this. But now we inject fluids, and due to the controller, we achieve a very slow energy dissipation. First of all, we stabilize the system, meaning that we avoid the earthquake. And second, we make it slide very slowly to a new equilibrium point that it is of lower energy and it is stable. So practically we avoid the earthquake.
That's amazing.
Thanks. And we have done also some experiments that we
and a little scary too, but
yeah, because we can provoke also earthquakes, but
exactly.
we are from the good side. So and without knowing the exact details of the system. But there are some conditions, and these conditions that also make TAN very, very interesting for this problem. And I will show you. Just this is the profile on the left. You see the open loop, meaning the velocities, the profile of velocities that were developed over the fault area. And this was the controlled one. The maximum slip rate was here. It was 210-3 meters per second. This was by design. We can make it even slower if we want. So, of course, these are academic examples. There are many open problems that they are still. There are optimization problems that they are interesting to solve, where you will put your wells, how you will put them. There are limitations by technological limitations by the pumps. All these are under investigation right now in the group. But all this work, provided that the friction coefficient is Leibniz continuous with respect to the states, it has a lower bound, and that elasticity and viscosity of the surrounding rocks are bounded, and also that diffusivity has a lower bound greater than 0. This, depending on the existing literature and physical arguments, these are logical assumptions. But if we want to, so the bounds exist for the physical materials, for the geomaterials that we are concerned. But if we want to have a more performant and optimal control, we would like to close the bounds to make them smaller and closer to reality. And this gives actually birth to advanced simulations of fault gauges. And fault gauges are granulated media. Filippo will say some works also in the next slides. Granulated material that they are quite complex to study, and also they are multi-physics couplings that they are activated. And unfortunately, we cannot do experiments deep down the Earth. So this gives actually the space for some interesting models in mechanics. And with that, I would like just to show you these are the rest members of the COCOE group that directly or indirectly participate with this. And I will give the floor to Filippo Masi to continue on TAN. Unless if you have some questions, would like to, I don't know, as you like, we can have some questions now or after.
Ioannis, I have a question on the optimization control. Has anybody, including your group, trying to do reinforcement learning, this type of process?
Yes.
People have been doing that?
Yes, we did that in a simplified system. It is a preliminary work. I don't know, you see here, this is a reinforced learning, and we did this to specify a controller, and it works. It is a bit slower. I mean, we have when we derive the controller analytically, we were confident that it will work. With reinforced learning, it is a bit more laborious, but maybe you can, I would be glad if you are interested to collaborate on this part. And what I think that reinforcement learning could be of use. These are some slides here to show you that you see here on the top left, you see that with the red line, the sleep. This is very fast in the control system, is the uncontrolled system. And with the controller derived with the reinforcement learning, it is almost linear and it is slow and we do as we want. Same for the velocity. It goes to very fast, 1 meter per second, more or less. While when we control it with the controller derived from the reinforcement learning, it does what we want. The same for the pressure here. I think what it could be very interesting, and there we really reach the limits of control theory for nonlinear systems, is when we go to discrete time control, meaning that we cannot update very fast our pressure. There, I think reinforcement learning can do quite a lot of nice things. So yes, to answer in short, we tried. It seems to work, and I think we can do much more things on that.
Thank you. Thank you.
So maybe if there are no other questions, maybe we can pass to Filippo. Ming Lang, I let you organize this. Okay.
Yep, Filippo, can you share your screen?
Yeah.
Thanks.
Okay. Thank you, Ioannis, for this introduction, and thank you for this invitation. So what I would like to do actually in this remaining part of the presentation is try actually to put, change this question mark in the title into an exclamation mark. That is how machine learning can help in earthquake control and fluid mechanics. So as Ioannis just showed us a few minutes ago, well, earthquake can be controlled in a reliable manner if we are able to compute and calculate somehow, well, the bounds of friction of a fault gauge of a seismic fault. Now, the problem is that how we can compute and calculate these bounds of friction, the friction behavior of a seismic fault, because the problematic is that we are having a system, a region in here, that is several kilometers under the earth crust, and that is extending over several kilometers, so that, well, experiments are impossible to perform deep down there. And so the only solution would be to, well, perform, reliable numerical simulation. And now the problem that kicks in at this point is that, well, this region that we want to model, well, is extending over several kilometers in length. And though if we zoom over this region, well, what we will observe is that we are actually dealing with multiple inherent structures. That is, we are dealing with what I define in here as complex materials. There are materials that possess multiple inherent spatial-temporal scales. And so the problematic in here is how can we model this macro scale problem, I would say, the fault gauge, the seismic faults, by accounting in a reliable way, of course, because we would like to control earthquake, by accounting for these multiple inherent scale. So, well, if I can rephrase this problematic, this means that we would like to solve a boundary value problem at the macro scale, our seismic fault. This means that we want to solve a problem like this one, where we have some balance equation, well, some boundary condition. And now the problematic is that we want to, to have a closure of this system of equation. Well, we need a constitutive law. That is, we need a link between the strain and the stresses. Now, what we can try as a first tentative is to, decide and design some heuristic constitutive model to, be fitted on some experimental results, numerical simulation, and so on. But as soon as you will try this, you will be aware of the fact that, well, heuristic constitutive models, well, are not, they do not allow us to account for these multiple scale that are here in this space of the boundary value problem at the level of the complex material. So what we see in the literature, and that we have seen also in the previous presentation actually, is well, the possibility of using multi-scale computational approaches. These approaches allow us to account for these multiple scales of the materials, and so finally to solve this boundary value problem by integrating a number of nested methods like the FEM or the DEM, or hybrids like the FEM square. However, independently of the approach that we want to use, the idea is to solve this boundary value problem, for which, of course, we don't have actually a closure for the constitutive model. So what we do is that, well, for every point of the structure, we will pass, if we are relying on a displacement-based formulation, we will pass the increment in strain, to, well, the microscopic scale that is defined by a unit cell, in which we will solve another problem that we call auxiliary. And by solving this problem, we will be able to compute what is happening at the micro scale, compute the increment in stress associated to the input increment in strain, and simply return this increment in stress to the original boundary value problem. Of course, as you can imagine, this solution of auxiliary problem needs to be performed for every point of your domain in here and for every time step. So the bottleneck of these approaches is the cumbersome and time-consuming ways with which the auxiliary problem is being solved repeatedly every time for every point of the domain. So what we have seen in the last few years is to try to get rid of the solution of this auxiliary problem, or at least try to speed up this simulation by using data-driven approaches, and in particular deep learning algorithms. So the idea is to have some data that may come from fine scale simulation or from laboratory experiments, and we use that to feed a neural network, for instance, that will retrieve for us automatically from the data the intrinsic link between the increment in strain and the increment in stresses. Now, though, as we know, well, neural networks are extremely good in extracting knowledge from data, but they lack of a framework based on physics. And it is at this point that the remedy of physics-informed neural network kicks in. That is what we're gonna look at today together, is the thermodynamics-based artificial neural network, or TAN, that Ioannis and I developed 2 years ago, that allow us to, based on the physics constraint that we can impose and enforce using pins, allow us to, well, finally retrieve the constitutive behavior, not only in a reliable, not only in an accurate way, so that we can speed up this multi-scale simulation, but also in a reliable manner, because we are relying on physics. Now, before going and looking at what these TAN actually are doing, we need to know a little bit what is the physics that we would like to enforce within them. So for us, in this case, the physics is actually thermodynamics. That is, we would like that our material, well, while it's deforming and, stretching and dilating, well, it's satisfying the first and second laws of thermodynamics. And you see here actually these two laws expressed in the form of a closest Duhem inequality. So we see that we have the mechanical dissipation rate, D, that needs to be equal to the inner power that is given by the contraction of the stress tensor times the rate of change of the deformation gradient minus the rate of change of the free energy, say, minus the rate of change of the absolute temperature times the entropy eta. And this, of course, needs to be bigger or equal than 0, second laws of thermodynamics. Now, though, as we were saying before, our aim is to solve a macro scale problem, boundary value problem. And though if we zoom over this region, what we will observe is some inherent microstructure that you see sketched in here that we can identify by the repetition in space of a unit cell. And so we are actually interested in understanding and predicting the material behavior of what is happening averagely on this unit cell. So what we can do simply is taking the closest Johann inequality that we wrote down before at the material point level and simply volume average it over the volume of the unit cell. Just notice that here uppercase letter are volume averages of the quantity that we defined above. So at this point, we have this volume average expression of the first and second laws of thermodynamics. And if we want to continue deriving some thermodynamic constraint that we want to put inside a neural network, well, we need to make a choice. And this choice concerns the state space. That is the set of variables on which the material behavior depends. And at this point, we would like to make a choice that is general as possible, as scalable as possible, that is not only valuable for seismic fault, for full gauges, but in a general way for a much broad class of complex material. So what we assuming here is that the material behavior is depending on a bunch of state variables. These state variables are the theta, the absolute temperature, the deformation gradient F, and an additional set of what we define as internal state variable, Z. These internal state variables are actually, well, added in this set of state variables to compensate for our lack of knowledge of what is happening down at the level inside the microstructure, inside the unit cell, but finally manifest itself as irreversibility at the macro scale. So as you can imagine, well, the identification of these internal state variables Z is not at all a trivial task. It will in general depend on the material and on the phenomena of which we are interested. Though I would like to ask you to make the abstraction, at least for the moment, about the physical nature of this variable Z. Let it be free, and everything will be clear, I hope, later on. So we have the state variable. The material behavior depends on this set of state variable. And we can continue by writing down that the energy, the stresses, the dissipation are state function. That is our function of this state variable. After that, we can simply, in a standard way, compute the time differentiation of the free energy that you see sketched here below. And by substituting these into the closest Johann inequality, the volume average expression that we derive, well, we will come up with a definition of what admissible thermodynamic processes are. So our processes such that we are, these three identities are actually valid. Now for continuing this talk, I will simplify a little bit more even the problematic, and I will only take two of these equalities. There are the first one concerning the stresses. There are the partial derivative of the free energy with respect to the strain, to the deformation gradient, and then a second one that is involving actually the definition of the mechanical dissipation rates. So basically, by only taking into account for these two equality, we are implicitly assuming that we are only modeling and interested into isothermal processes. Though the approach is general, the framework is general. So if one day you want to see what are the effects of temperature, you just get and take into account also for this equality. So we have now the physics, that is the thermodynamics, and we want to see how we can translate it into a physics-informed neural network. For us, this will be a thermodynamics-based artificial neural network, TAN. So TAN, they rely on an incremental formulation of the material behavior. This, we know the material state at time t. We know the increment in deformation that we want to apply to our material. And we want to simply predict the future state at time t plus delta t. So as eligible candidates as inputs, of course, we have the material state that are the strain, stresses, and state variable at time t, plus the strain increment. Now with TAN, well, the architecture will resemble in a schematic representation to something like this. So we have basically two neural networks. The first one on the left is basically taking these inputs and is predicting the evolution law, that is the increment in the internal state variable, Z. From this prediction, we can simply compute the update state variable, ZT plus delta T, that together with the update strain deformation will be the input of a second network. This is a shallow network because basically this network will predict a scalar, that is the free energy. Though at the end of the day, as we said, we are interested in deriving the constitutive relationship. So, well, this is pretty straightforward in TAN because we will simply enforce the thermodynamic constraint that we derived previously. That is, the stresses are the derivative of the free energy with respect to the deformation, and then something that is extremely similar to for the dissipation rate. So this is done, of course, by differentiating the output of the network with respect to its inputs using the automatic differentiation technique. So if we got a look on the gradient, so we have the first gradient in here that will be backpropagated up to the inputs, one of the inputs of the second neural network, while the mechanical dissipation output will be backpropagated up to the output of the first neural network. So actually these two thermodynamic constraints will allow us to, well, optimize and train in a proper way the entire network that we see sketched in here. This is done by training the architecture, as you see depicted in here, by minimizing this loss function with a gradient descent algorithm. So we have four principal terms that are actually the four outputs of the network. So these are, I would say, a first generation of TAN, and we compare them with state-of-the-art artificial neural networks, so without physics, for material modeling. So you see very rapidly on the left, the first column is just the training curve of TAN that goes all together. And then you see on the right instead the other columns represent the prediction of TAN with respect to standard ANN. So the first column represents the prediction for a elastic hyperplastic material for actually value that are close to the training domain in terms of stresses, free energy, and dissipation rate. The orange is TAN, the gray, dark gray, it's actually ANN. So you see, I actually is not able to satisfy the physics. And then when we go to prediction, to make prediction far from the training domain, we are several order of magnitude outside of the training domain. The training domain, if I want to depict it here, it will be just a point, okay, the first one. So we see actually how TAN are extremely well in generalizing and extrapolating the result. This thanks to the physics, to thermodynamics, and this while of course being always reliable in terms of the thermodynamics that is being respected. And then the last column is just to show that to solve the original boundary value problem that we sketched before, we need basically to compute some higher order gradients. That is the Jacobian, that is the partial derivative of the increment in stresses with respect to the increment in strain. But our delta sigma in here actually is already a gradient computed as a gradient inside TAN. So this is a second order gradient that is only computed not during the training, but only in recall. And you see how it actually is performingly very nice compared to TAN that are completely wrong. So for this,
Filippo, I have a question.
Yeah.
If you go back to your neural network,
yeah,
the architecture, how do you impose the inequality?
Sorry?
How do you impose the inequality? Are you using a soft constraint? It's a built-in? How do you impose the inequality?
I will to the dissipation you're saying, right?
Yes, exactly.
Yeah. I will just impose him that it needs to be positive during the training, and he will understand that basically that if he's predicting something that is negative, it will be absolute value, so it will be extremely high as prediction, and not around 0. So he will understand that there is something that is happening if it's bigger, smaller than 0, and it will get it. But in general, I would say if you are feeding the network with even with thermodynamic consistent data set, the fact that the dissipation is bigger than 0 or equal to 0, it's intrinsically guided by the network.
But are you checking it afterwards?
Yeah, of course. You sorry, just to have a look. You see here, you have these two elements in the
always positive.
last row. It's always positive and on the branch where it's supposed to be. While the A and N, you see they go slightly negative, and when you go to ask him for prediction outside of the training domain, so in here in this scale is basically 0, but is the same value basically. While the A and N that are not based on physics, they give you. I mean,
so you're not using a Lagrange multiplier to impose it.
No.
You just got lucky.
I don't think it's lucky. It's a matter of lucky. But yeah, I mean,
if you don't have the right network, that if you don't get the right network, that will be violated because it's not imposed.
It's not imposed, but it's imposed from. Sorry, we'll come back. It's imposed from these definitions, from these gradients. So basically, if you got right the energy and you got right the evolution of the state variable, that is the first neural network in TAN, well, it will got right that these things can only be positive. So I don't think, I mean, I'm pretty sure that is not really so much depending on the architecture, I would say, of your network. I say that. But
the accuracy depends on the architecture.
Yeah, but I'm saying that it's not just something that's I've been lucky in finding the good hyperparameters, the network understood somehow, and this is magic. We say that it's it's inside this formula actually, this expression, the first part, that is understanding that these things need to be positive defined, and if it's not, then it might be to some noise in the data set, but it won't get that noise. Indeed, when we put some noise either in the dissipation, either in the stresses, either in the input of the network when training, the TAN are extremely robust. We prove this with some comparison, and basically I will go just a little bit ahead to show you something. Yeah, here we are predicting something with a noise in the training dataset, and then we are asking for prediction. So it's basically the TAN that has been trained on non-noise data, and then the TAN trained on noisy data. And you see that basically the prediction they just overlay. I mean,
the noise is on training data or on the testing data?
The training data. Training data.
But the real test is to do it on noise testing data with a little noise.
I'm taking TAN that has not been previously trained, and I will train on noisy data sets. So if we get a wrong, it's supposed to get a wrong answer in principle. That is the noise. It's supposed to be guided by the noise together with the thermodynamics. Though what we see is that it basically, I don't have in here the training curve, but it will stop the noise was on the stresses. So it will stop to a plateau that is not a very small error because you see the noise, and it basically is not learning the noise because it wants to satisfy the physics. So when we then make the test like this one, in that case, there is no noise in this test because we are simply, I mean, there is noise in the inputs of the noise at TAN, but the prediction are, I mean, like it was not working on noisy data.
Right. So we usually look at a little different. In other words, you train the TAN.
Yeah. Then
somebody mistypes some of the input in the testing data.
Yeah.
It has a little bit of a noise. What happens then? In other words, the noise would be on the testing data, not on the training data. Although you train it on the clean data like before.
it means that you the question is how you will be sure that when you make
your system stable? That's what the question is. Is your system stable?
Yes, I think so. I mean, it depends on how good basically is the choice of your state variable, I would say, in that case, because it depends on what noise where you will put your error by copying pasting your data. But in general, the system, I mean, the part on the string is pretty evident, it's pretty straightforward. So the only noisy part that I can see coming is for stresses or state variable, that. So I'm pretty sure that this is still stable. We didn't test it properly. I mean, besides from the training on noisy data. But
yes,
yeah,
if you allow me, Filippo.
Yeah.
It cannot in predictions violate the relations that you showed before. So it depends what we call stable in this sense.
Yeah.
So if it learns, this is why when the training data are noisy, then it learns the psi function and the D function and the Z quite well. So this is why it does predictions that they are okay. Now, yes.
Yeah, but it's like something like saying as is feeding himself iteratively at every time step. It's like assuming, yeah, your original time at 0, let's say, is a wrong time, and from that you ask Tutan to make a prediction will be driven by this noise and will propagate, or will be there and stay there. So in that case, I would say that yeah, it will stay there and will be stable. This is for sure.
I have a question.
Yeah.
When you insert the noise, you check if the noise is giving positive dissipation, because.
What do you mean in general? I mean,
no. When you insert the noise, we insert your general noise that can give negative dissipation too. Right?
Yeah.
You check this, right?
Yeah. This has been tested, of course. This was one of the set of the test on noise, actually, to put a negative dissipation and see if you can learn it.
Okay.
Without, though, in that case, put the positive constraint on it, because that's the thing. If I only ask to output the absolute value, it will never be negative, and so there is no deal. I mean, there is nothing to be tested.
So I have other question concerning the history of string. What you do is like a pure test, is like a pure interaction, pure shear, or you are like mixing.
Okay, so I see it as a 2 question. First answer, there is no history. There is no history, because
there's no history. Okay,
there is no, and that's the thing. That's why it's stable, actually, finally on time.
Okay.
On noise, because we have the state variable. So basically, the intrinsic assumption based on thermodynamics is that your material state at time t, any time, from 0 to minus infinite to infinite, is characterized by this variable. And so, as you don't have time history, for the data generation, it depends. If you are able to generate random states, then you can generate random states. If you are in the usual case for very complex material, for very complex system, you won't be able to know exactly the constitutive law, because what we are searching for is actually this one. So you can do random loading path in the history, and then what we do is just we take a couple of these path, and these will be the time t and the time t plus delta t, and we shuffle everything. So there is no more time. We don't need it. Okay. It's not a recurrent neural network or something like this.
Okay.
Okay. So I will continue if there are no other questions. So yeah, so I was saying, okay, to just resume this thing. So we have seen that TAN are, for material that we know, they allow us to have thermodynamic admissible prediction. These within the training domain, of course, but also the training domain. These TAN have high generalization capabilities. They are robust to noise in the training datasets, but there are 2 issues in this first part of the presentation. That is the fact that as we are dealing with physics-informed neural network, well, we are dealing with higher order vanishing gradients. That is, well, you should take some attention in selecting the appropriate activation function. And the second issue is the fact that, well, we need to identify somehow the state variable, this internal state variable Z. And this is something that is not trivial at all for the, well, the example that I show you up too far, these internal state variable were actually the reversible deformation. Though the we would like to get rid of this a priori identification, we would like somehow that can select the state variable and then play with them without needing any interaction from the user. So the question is how we can finally identify the state variable, but we would like to identify the state variable in a general way, in a scalable way. That is, we would like to, identify state variable that characterize the deformation of bones, muscle, metamaterials, granular material, and so on. So how we can do that? Well, the solution is to define a new quantity that are the internal coordinates. I define internal coordinates here, all those variables that characterize the microscopic state space. That is the displacement field, the velocity field, the momentum field, all the internal degrees of freedom of our microstructure. So as you can imagine, when we are dealing with these internal coordinates for a complex material, like a bones or like a granular material, well, we are dealing with a variable that span a high dimensional space. And if you are dealing with them, well, we might not be computationally efficient, and we are searching not only for reliability and accuracy, but also for acceleration, computational acceleration. So at this point, we could think of using reduced order model, like an autoencoder, to feed it with some internal coordinates that we have that is our microstructure, so snapshot of the microstructure. And by minimizing the reconstruction error of the decoder, we would like to, cross the finger and hope that this low dimensional representation, this intrinsic representation, R is coinciding with Z, that are the internal state variable. Though in general, this is not true for an autoencoder like this or any other reduced order model that you might prefer and use, because well, these modeling here won't be aware of the physics, the underlying thermodynamics of the problem that we want to study. So how we can do that? Well, to answer to this question, I will go back to the previous scheme of time. Now, as you can see here, the problematic is that we don't know this internal state variable, so we basically cannot train the network because we won't have data. We don't know what to minimize in here. So the solution is to change and pass to the internal coordinates that are that we use to feed an encoder. This time, the encoder, rather than going directly to the decoder, and this the innovation, I would say, is it will give us put some latent dimension that are not Z, even if here I identify as Z, they will become, but not at this moment. So we will use this latent dimension to feed the upper part of the network as before. And if we want, at this point, we can make take the output of the first neural network that are the updated latent dimension without knowing what they are for the moment, and put them to feed a decoder that will give us the evolution of the microscopic states, that is the internal coordinates, the evolution of the internal degree of freedom of our system. So if we look back at the thermodynamic constraint and the gradient, basically we have the stresses will be back propagated up to the strain as before, while the dissipation, well, it will be back propagated up to the output of the encoder. So this will allow us actually to vary and modify accordingly a big part of the network. And then we put additionally some constraint still formulated in terms of gradient of the output of the decoder with respect to the encoder, because we observed that basically they allow us to be much more performant in the error. And so at this point, we simply train this network that you see scheduling here by minimizing a loss function that's slightly different from the previous one. And at this point, once the training has been performed, of course, it should be successful. And if so, we will be able to have some latent dimension, find some latent dimension, such that we can predict the free energy and the entire constitutive response based on thermodynamics. That is, we will come up by identifying in a supervised manner, even if it's thermodynamic driven, well, a set of admissible state variable. And so at this point, we will have this encoder that can generate the state variable from the knowledge of the internal coordinates. And so that we will simply get rid of them because we don't need them. They are spanning high dimensional spaces and they won't be computationally efficient. So that we will have the state variable that we identify, to which we can describe the entire material behavior with tan. And though at any point, if needed, we can ask to the trained decoder to take the prediction of the state variable that we identified and to reverse it back to the microscopic states. So this is actually a very recent work of Ioannis and I. And I would like to show you some benchmark. So a first one that is involving lattice structure, either regular on the left here or irregular on the right. You see here how actually we are computing the stress tensor and the deformation tensor. To study this structure, their behavior, we develop an in-house finite element code so that we have high fidelity simulation of what is going on in this microstructure, in this structure. And then we simply train the TAN on micromechanical data sets generated from random loading path on this cell, for example, just to have two examples in here. And then in here you see some of the prediction for an unseen loading path. So in here you see the prediction of the TAN with respect to the high fidelity solution in terms of stresses, of energy. You see in here the evolution of the state variable that TAN managed to identify. And then these, of course, at any moment can be, well, decoded to characterize the evolution of the microscopic fields of the lattice structure in this case. And then, well, TAN, they do not only inherit all the advantages that we have seen before, but in this case, they allow us also to have a very reduced computational cost with an acceleration that is more than 3 orders of magnitude compared to the high fidelity model. Though at this point, so we solved basically the behavior of the unit cell. Though at the end of the day, as I started this talk, we want to solve a boundary value problem at the macro scale. So we are here, actually, we solved just this problem. We would like to solve the big problem. And so how we can do that? We will do this in with a new approach that is the FEN-TAN approach that we'll look later on, and is basically relying on the asymptotic homogenization theory. That is an homogenization theory that has rigorous mathematical basis and allow us actually to develop this homogenization and actually be able to compute the bounds of the error that we are committing with this kind of approximation. So if I can rephrase this, we want to solve a macroscopic problem given a certain volume, that is this volume in here, that is an heterogeneous material that is characterized by a spatially quasi-periodic repetition of a unit cell that you see sketched in here, Y. So, of course, this microscopic boundary value problem will consist of some balance equations, some boundary condition, and our constitutive load that we don't know actually. And at this point, within the framework of asymptotic homogenization, we assume that we can separate the scale, that is the macroscopic scale, x, of the macroscopic problem, and a microscopic one, y, that is x divided by epsilon, where epsilon it's the size of the unit cell. And at this point, well, the differentiation operator basically with respect to spatial coordinates in the original problem reads like this by applying the chain rule with respect to the separate variable. And at this point, we can simply develop an asymptotic homogenization of the displacement field of the original problem with respect to the epsilon term, to the cell size in here, up to a given order. We take these answers, we replace it into the strain tensor. We will get to an asymptotic expansion of the strain tensor, which can be substituted inside a stress tensor. So we will develop once more in here an asymptotic expansion in terms of epsilon for the stress tensor that can be replaced in the balance equation that we have in the original boundary value problem. And this will give us, as you can see in here, this equation that needs to be valid for every epsilon that tends towards 0, plus of course some expansion, the expansion of the boundary condition defined on the microscopic original boundary value problem. And this will give us so that all these terms that are factorizing epsilon term, that needs to be 0. And so it will give us actually a cascade of partial differential equation. They are infinite actually, and then we need to truncate to a certain, of course, this is up to us, to truncate to a certain order or approximation of our epsilon. At this point, we can just to redefine the volume average operator that we have seen at the very beginning over the unit cell. And by cutting up to a first order approximation in terms of epsilon, we come up with two boundary value problem. The first one on the left is the auxiliary problem that we were looking at before, that is defined over Y, that is the unit cell, and that we are able to solve, and we solve just now with TAN. On the other way around, we have an incremental homogenized boundary value problem that will be acting on a volume that is an homogenized material, and will allow us basically for epsilon that tends towards 0 to approximate with high accuracy the original macroscopic boundary value problem. Now, the problem in this theory, or in general in multi-scale simulation, is the fact that the solution of this auxiliary problem, well, is low and extremely expensive. So we would like to get rid of it. And so to do so, we use actually what I define in here as FEN-TAN approach. So the idea is to model, with a finite element modeling here, for example, an homogeneous material in which at each Gauss point, we will replace the constitutive behavior by the trained TAN. Though in addition, thanks to the fact that we are able to find the link between the microstructure and the state variable, we are basically able, by decoding the state variable, to recreate the microscopic field of the microstructure, and so basically evaluate their evolution within the large scale domain. So this is the approach. Some application involving lattice structure, as we have seen before. So we have a structure in which we are applying a torsion of the upper bounds, and we are comparing the FEN-TAN approach with respect to the high fidelity. So we are modeling the entire microstructure, the proper scale. And you see on the right the simulation result in terms of the displacement of a control point, the dissipation rate, and the energy. As you can see, as soon as epsilon, that is the size of the unit cell, tends towards 0, well, the FEN-TAN approach result rapidly converge to the exact solution of the high fidelity problem. This thanks to the rigorous mathematical background. And so thanks then to the fact that TANs have all these benefits deriving from the fact that we are enforcing physics, thermodynamics, we don't not only have accurate and reliable simulation, but we are able also to have computational acceleration that are more than 2 order of magnitude up to 3 order of magnitude. In here, still another application, still of a lattice structure. We are still applying a torsion, but this time is cyclic, so it's changing in time, and we are torquing around 0 in different direction. And at the end of this step, we simply unload the structure that will reach a new equilibrium point, more or less around 0. So in here, you see the evolution of the displacement field as predicted by the FEN-TAN approach. And here you see the comparison that is barely impossible to see between the FEN-TAN approach and the the exact solution. At this point, it's pretty interesting to evaluate the evolution of the state variable that we identified with TAN in a supervised manner. So you see in here the evolution of one of them. Blue means 0, red means different from 0. As you can see in here, interesting is in the unloading part. So after unloading, we have some state variable that are different from 0. Well, this means that TAN were able to identify state variable such that, well, they are describing microscopic phenomena that finally manifest themselves as macroscopic irreversibilities. We are not applying forces or displacement in these, though we have state variable different from 0. These are permanent deformation. So up to now, I just show you something about lattice structure, the application to lattice structure. This is why, because, well, we are actually applying TAN for geomaterial right now. I will show you some first results. So what we have in here is that we are modeling granular material with a discrete element method. You see here the grain, spherical one for the moment. They're interacting one with the other. So we generate data by applying random loading patterns before and then shuffling. And then in here, you see some prediction of time with respect to discrete element methods here in terms of stress with respect to strain. And here you see one of the identified, just to take an example, state variable that is able to characterize the loading and unloading of the material. So once more, we are able to model the irreversibility in a correct way, and such that basically we are finally encoding more than 300 degrees of freedom with only 10 state variable. This is a very huge compression factor. So at this point, I think time is finishing. So I would like to conclude by saying that STAN, within the earthquake control and coldquake, they will allow us in the near future to perform large simulation of real fault system. These everything in a virtual environment that is based on physics and data-driven neural network that will finally fit on a laptop because of the extremely reduced computational costs. You won't need a supercalculator, a supercomputer to perform such simulation. So I would like to finish by thanking you for your attention, and we are looking forward to hearing your question.
Great, thank you very much. This both talks excellent, Filippo and Felipe. Great. Are you familiar with the generic framework of Oettinger?
Yeah. Yes. Yeah.
Because for dynamical systems, you're talking about static systems. For dynamical systems, we both Nat Trask, that he had to leave, but he was asking these questions earlier, and then ourselves, we recently published the generic informed neural networks.
Okay, but
so that's for stochastic.
Yeah, this approach though is also valid for dynamic, huh?
Yes, for dynamic.
Yeah. This is also the state variable here approach is also valid for dynamic. I mean, there are no contradiction, I would say, in the approach. We didn't get tested for problem with some inertia and so on, but I'm pretty positive about it. But yeah, it seems interesting. I don't know if you know the work of Kinesta.
Yes. That work. Basically, we compare against that work, and we compare against Nat Trask, who left, and Ioannis here is one of the PhD students. That's why I was insisting on how you impose the constraints. For example, the work of Pancho fails very quickly when you try to predict outside the distribution, because the constraint is not good enough. Nat Trask tried to introduce some structure, but actually it depends on what network. I don't know if Yongjon Shin or Zhen Jiang are here. They're the authors of this paper. And then we came up with a theory that says how you actually should do it, and we have a universal approximation theorem with the generic framework that in principle it should work also for your systems, because it doesn't really care about the scales. Yongjon, are you logged in, or are you? I don't know if you sign off. Yongjon Shin, maybe sign off.
And the internal coordinate, if I may, the internal degree of freedom in the generic, you work with them, or you try to compress them?
So we have, in the generic framework, we have this matrices M and S, so that has this certain properties. So that's how you describe the system. We've done it for different. The most difficult problem was when you have a stochastic problem, because you're trying to extrapolate in time, and you have very short window of extrapolation, and using the correct imposition of constraints, it can take you for a very long time, the extrapolation. So we compare with other frameworks that don't have that. But I was looking at all your dissipation. They look fine. So
for the moment, yes.
And I said you get lucky everywhere, so.
I don't think, but yeah, I will see. If I will find a material that give me negative dissipation, I suppose not. I will tell you.
I have a question for both speakers, which you come from solid mechanics and so on, but imagine that you have some fluidic or plasticity inside fact, or any coarse grain, right? If you look at the rigorous formulation of the Morris-Wanswyk from statistical physics, it tells you that every time you coarse grain a system, you have three contributions. One is the conservative, another one is, of course, the memory integral, which has to do with the covariance times, let's say, the pressure, but it's a time integral. So that's the history term. And there's also a random force that has to do with the fact that you can never reproduce the lossy information, right? You can never reproduce after you coarse grain. You have to account with a term that does not depend on the result variables. I pose this question so there's a method we have sort of co-developed. It's called dissipative particle dynamics. It does that. It conforms to that. There's some technical details. Peridynamics, for example, does not do that. Okay, I asked Sue Sealing what happened to, at one point, I organized a one-day conference on Morris-Wanswyk, dissipative particle dynamics, and peridynamics. But all these homogenization methods ignore that important, basically the fact that you get long-range interactions in space-time, it turns out, when you coarse grain. But not you, I'm not talking about you specifically, the speakers. I'm talking about the community. Yeah. The community, you're all happy about it. And
not really, because it gives place to the generalized continua that they can take into account long-range interactions.
Yeah.
And I'm not talking only about the Kossera continua, that they have also some very, very nice properties for regularizing some problems, especially related to strain localization and softening, that we don't present here.
Yeah.
They are also the micromorphic of first and second order, that you can exactly have these long-range interactions. But until now, there is not a, let's say, a rigorous mathematical way of doing homogenization with this media. We have ways that they are quite good, and we get good results with some energetic approaches, but there's not this scale separation notion in this media. So the classical asymptotic homogenization approaches fail, at least.
Yes, of course they fail. That's what the
But if I may, though, well, what we presented in here, we were focusing on the unit cell. Yeah, you see my mouse on the unit cell in here, and then basically using homogenization to solve the big problem. Though basically with the framework that we have seen, TAN, well, you are basically able to take all your long-range interaction by solving directly this problem. Basically, you can model the behavior of the entire structure just in once, without needing of multiple scale. You will be able to encode the behavior of this macrostructure by finding some state variable that will be averaged somehow. It will decide how, because it needs to fit everything. But I don't see. I mean, what I want to say is that we are not necessarily constrained to homogenization. That's my answer.
Filippo, there's no separation of scales.
Yeah,
only the classroom. Only the classroom.
Yes, of course. What I would say indeed is that basically in here was finally using separation of scale, but basically you can use TAN without separation of scale, without using asymptotic homogenization. You can model the entire system in a once.
The TAN are used to learn the constitutive behavior of the material. That's all. Then the question is, what would be a rigorous mathematical scheme for doing asymptotic homogenization in micromorphic continua? The work stopped with the seminal works of Samuel Forest and Karam-Sab for Kossera continuum, that they show that you retrieve from even if you have a Kossera at the microscale, you retrieve a Cauchy when you take the microstructure to 10 to 0. But there is a small detail there, and we are studying this with a student of mine on because in the end of the day, these are asymptotic approaches, and the epsilon that we define classically in this framework of asymptotic homogenization as the ratio of the unit cell with the structure. This is one definition, but there's other definitions based on the moduli of the materials. And this, when we have strain localization, these are not small. They are
inclusions, yeah, inclusion.
Yeah, there are some things there that proper mathematical analysis could give some more light. But yes, just to join to Filippo was practically saying that this is at the constitutive level. So if we enhance and enrich the deformation space with some other measures, deformation measures, still the same approach could be applied. What I would like to ask you, George, is maybe do you think that this new publication that you have, the generic informed network, the generic informed framework for neural networks could be helpful in this work? How we could use this?
I think so. Not for what you're doing. You're doing great. So there's no. But I think for maybe in thermoplasticity or viscoelasticity, some like time dependent, whether it's histories and so on. Jan, are you? Oh, no. Let me see if he's here. Yeah, he's here.
Yeah.
Maybe Jan, maybe you can say something. You can answer Ioannis' question. You can turn on your camera and answer.
Yeah, sorry. I was sick and at home today, so like maybe I would not turn on my camera.
Okay.
So sorry, what was the question again? Like
if your paper, if it could be applied in the same, you know how you impose the structure. Exactly, you impose the constraint exactly. Well, you're similar to what Filippo showed, but then we have the theorem. So because you take the neural network on the derivative of, just like your formulation, if you could apply to the problem that Filippo showed.
Maybe Filippo, I don't know if you can show the network, the structure.
Yes.
Maybe, yes, if it is.
Wait. Or I can take the simpler one back.
yeah, so basically like so for our method, like I think we need like we need to have like the state variables. Like currently, like we need all the state variables that can I mean, like so if the system can be written in a generic formalism, then like our model can work. But like the restriction is that we need the all the state variables in the whole that can describe the whole system. So so for
these
these
state variables could be, if they are a lot, there is a problem.
Yes, so maybe in that case we need to do a dimension reduction, but that is still like some ongoing work.
Filippo has this here. Yeah, you see it there. Yeah.
So
Yeah,
basically,
you see the dimensionality of the system can be very high, but we are interested only in this part of this high dimensionality that contributes to the energy, the dissipation, the stress.
Yeah.
Yeah, I see. Yeah, so
I think Paco is doing something like this, huh? It's still encoding these internal degree of freedom to find finally the structure of generic, huh? I think they're doing something like this, if I remember well.
Yeah, but Paco is not here.
Yeah, but just to, brainstorming. Yeah, that's nice. And for the dissipation, how you actually are able to impose the constraint that should be positive?
So regarding the dissipation, like we incorporate the dissipation fluctuation theorem. Like not like so we in the generic formalism there is this kind of theorem, and because we strictly enforce the generic formalism, so that is also enforced in our formulation.
Okay. Thank you.
But take a look, Filippo. That's
yeah. I will definitely.
If you're familiar with Pancho's work, then that you'll follow it. Thank you all for coming. It was a good discussion today. It was so happened that we have 2 talks on homogenization, which is we didn't have that before. Minlang, did you plan it, or was just the planets aligned?
Well, it just happened, so I didn't.
Okay.
Yeah, I specifically told Enray, and this is a solid mechanics day, so you may want to pay more attention to that. And it was a festival. Yeah.
Okay. All right.
Yeah, it was nice.
Okay. And I think one of us reviewed your paper and we gave it favorable ratings, but we're not supposed to talk about it.
Oh, great news.
Great news.
Thank you.
Okay. All right, everybody. Minlang, maybe you can close this.
All right. Yeah. Everybody. So this is the end of this week seminar. Everybody, take care. I'll see you next week. Bye.
Thank you.
Bye-bye.
Thank you again.
Bye.
Bye-bye.